Solids are encountered in everyday life. In fact, it's the phase we're probably the most comfortable with. Here we seek to describe the different classifications of solids that we encounter in the real world. When we describe solids, they can fall under one of two categories. The first being amorphous. Amorphous solids lack any consistent order or arrangement to the molecules that make them up. They're kind of haphazardly strewn throughout the molecule or material and lack an overall organization to it. On the other hand, we have crystalline solids, which do have a repeating array of atoms or molecules which is systematically built on top of each other. We'll be examining crystalline solids for the remainder of this discussion. The first type of solid I'd like to describe is a metallic solid, that is, metals and alloys. And we describe metallic solids as being held together by a delocalized sea of valence electrons, or basically one gigantic electron cloud for all the atoms present. The second classification would be an ionic solid. These are solids that are held together by electrostatic attractions, that is, positive and negative charges being attracted to each other, in such a way that each positive charge is as far away from other positive charges. Or if you look at the diagram of sodium chloride there, you see that each sodium atom, which is purple, is as far away from other sodium atoms as possible. In fact, it's surrounded completely by chloride ions. The third classification of solid is a covalent network solid. These are solids which are held together by covalent bonds. There's no intermolecular attractions in these molecules, rather they're just one large molecule. The fourth type of solid is a molecular solid. These are smaller molecules which are held together by intermolecular forces. In fact, the degree and strength of their rigidity is a property of what kind of intermolecular force present and how strong it is. Polymers, also known as plastics, are long chains of atoms where there is a repeating pattern to the chain. If you look at the monomer on the left at the bottom, you'll see that in the polymer of it, you get this repeating form of this monomer done over and over and over again in this pattern. And polymers have a repeating pattern, but not necessarily a consistent length. Nanomaterials are at the current cutting edge of our scientific research and focus on materials and the properties they have when they're less than 100 nanometers in size and consist of less than 1,000 atoms in it. They're relatively interesting because they keep the atomic nature of their properties rather than getting swamped out by what we call bulk properties of atoms. And that creates some interesting chemistry and properties that we can use to exploit. For example, LED lights are one type of application of nanomaterials.